Hello friends, so this is the continuation of the video which is part 5, where I have already discussed 6 problems on nucleophilic substitution reaction. So now I will discuss some more problems on the same topic. So the first problem here is the cis isomer of 4 tertiary butyl cyclohexyl bromide, that is cyclohexane. At 1 and 4 position there is 4 tertiary butyl group and bromine. It is reacting with PHSNA, that is sodium salt of thiophenol. Phenol is PHOH, thiophenol is PHSH, and the sodium salt is PHSNA. So this molecule reacting with PHSNA at a much faster SN2 rate compared to its trans isomer, because these two groups, the two groups tertiary butyl and bromine, these two have a cis conformation or a trans conformation. So first we will see here, this is the cis. So here you can see the tertiary butyl group and the bromine, both are on the same side. Now if you draw the chair conformation, the rule is at 1 and 4 position, both the groups, that is one of them should be equatorial, another one of the group it should be axial. Now tertiary butyl group being very bulky, it always remains equatorial position. So it is locking the position of Br at axial always. Now if it is trans, then the rule is that both the groups, either it will be equatorial or both of them will be axial. Now again tertiary butyl group, it always prefers equatorial because it is very bulky. So again it is locking the position of Br in the equatorial form. This is trans. So in the trans, the nucleophile, when it is attacking from the opposite side of Br, it is not facing any steric hindrance. On the other hand, when it is trans, the nucleophile is attacking from the opposite side of Br, it is facing steric hindrance with the 2 hydrogens at 3 position and 5 position. So the conformer with axial leaving group, it reacts more rapidly than the conformer with the equatorial leaving group. So that is the reason that cis, it is reacting at a much faster SN2 rate. Another reason you can also consider, that is the ground state energy, that is just before the reaction. Suppose the starting material, one is cis, another one is trans. So if cis having energy, if it is the energy profile diagram, if it is the energy of cis, suppose it is the energy of cis, because it is in axial, so the ground state energy, it is always higher corresponding to the axial. That is, I am talking about the trans. So ground state energy of the axial isomer, which is nothing but the cis isomer, it is comparatively higher than the trans isomer, because in trans Br it is in equatorial, obviously it will have less ground state energy. Now if you consider the transition state, which is fixed, the gap between cis and the transition state, it is low compared to the gap between the trans isomer and the transition state. That means the activation energy for the axial isomer, that is the cis isomer, it is being higher than the activation energy of the equatorial isomer. Sorry, I made a mistake here. It is actually correct. That is the ground state energy of the axial isomer, that is the cis isomer, it is higher. The activation energy of the isomer is relatively so. So as the cis isomer, it is already having higher energy compared to the trans. So this activation energy, obviously it is lesser than the activation energy of the trans. So that is why cis, it reacts faster compared to the trans. Cis reacts faster compared to the trans. Fine. So that is all about this problem. Now come to the second one. So second one, here we have total 3 molecules, and the question is that which of the 2 halogens will be more reactive in an SN1 reaction. So in all these molecules you can see there are actually 2 leaving groups, and both the leaving groups are same atom. So come to the first molecule, where we can see 2 bromine atom. So bromine atom 1 and bromine atom 2. So which of these bromine atom, it will be taking part in SN1 reaction? Now if it is bromine 1, the positive charge will be here, which is primary. But if the bromine 2 is leaving, then the positive charge it is on this carbon, which is 3 degree. So obviously bromine 2, it will be beta leaving group. So this halogen, that is this bromine atom, will be more reactive. Now come to the second one. Here the carbocation, if I1 is leaving, this is the carbocation. If I2 is leaving, this is the carbocation. Now carbocation at for the, that is the left hand side carbocation, it is allylic 1. But the right hand side carbocation, that is not allylic 1. Now allylic carbocation, because of resonance, it is always stable. So here I1 will be more reactive compared to I2. The third structure is bicyclic. So here bromine 1, if it is leaving, you will get a positive charge here. If bromine 2 is leaving, you will get a positive charge, which cannot attain planar configuration. So that is, it will not be stable at all. So that is the reason Br1 will be more reactive in SN1 reaction. Now again we will see 3 substrate, but now the question is, which of the halogen will be more reactive in an SN2 reaction? So which of the 2 halogens will be more reactive in an SN2 reaction? So in the first molecule, you can see again the same molecule that we have already seen here. So bromine 1 and bromine 2, if you are removing bromine 1, you will, that is, though it is not SN2, so still if you consider, that is the, just consider this portion. So this is primary halide, isn't it? But if you consider this portion, it is tertiary halide. So obviously it will be better, more reactive halogen among these 2 bromine atom. That is Br1 will be winning over Br2. Now come to the second one. Again same molecule as we have seen in the first case. So I1 and I2. Now you can think that in both cases it is primary iodide, isn't it? But here the thing is, here double bond is present here, which is close to this center, unlike this side. So what will happen? The transition state, there will be a partial positive charge. It is not full positive charge like SN1, but there is partial positive charge. So this transition state, it will be relatively more stable. And why it is relatively more stable? Because it is stabilized by the adjacent double bond by pi overlap. So again here I1 wins over I2. Now the last molecule, here again both are 1 degree. If you just separately look these 2 sides, but if you compare leaving group, we know that Br is beta leaving group compared to Cl minus. Br minus is beta leaving group compared to Cl minus. So here Br will win over Cl. Okay. Next we have a large question which will take some more time. Account for the stereochemical course. Stereochemical course means we have to determine whether what is the stereochemistry of each of these unknown product A, B, C, D, E, etc. And also we have to give the 3D structures of all these compounds starting from A up to E. So the first molecule, that is our starting material, is R2-octanol. So this is a methyl group here. So this is R configuration. So in the first step we are using tosyl chloride and pyridine. So this is a full structure of tosyl chloride. So in presence of tosyl chloride, the lone pair over oxygen, it will attack the sulfur and Cl will be removed. So the structure that we will get first, that is our molecule A. So this is A, this one. The name is also given. Now see the configuration, it is same, it is still R. Why? Because the chiral center, this is not disturbed at all. The reaction is happening here. So obviously it will be again R2-octyl tosylate. Next what we are using? We are using NaN3. So NaN3, here the nucleophile is N3 minus. So OTS is very good leaving group. So N3 minus, it will attack from the opposite side. So now there is inversion taking place. And also see the solvent, it is polar aprotic. So that is why it is SN2. So now we are getting inversion. Now it is S. Next we are using H2PT. So this is a hydrogenation reaction that will take place. So N3 will be converted to NH2 group in presence of metal catalyzed hydrogenation. Platinum is the metal here. So now N3, it is simply changing to NH2. So here also there is no change at chiral center. So configuration will be same. Next what we are doing, we are using, that is after C, we are using sodium nitrite in acetic acid. Now sodium nitrite in presence of acetic acid, it will generate HNO2, that is nitrous acid. So in presence of nitrous acid, there will be formation of unstable diazonium salt. So this is unstable diazonium salt, where N2 will be removed. N2 is very good Lewin group because as a molecule nitrogen, it is very stable molecule. So this group will be removed. And finally see what is written, D plus E. So after this step, there are two products. So when nitrogen will be removed as Lewin group, we will get a positively charged carbon, that is carbocation. Now there is change taking place at carbocation. That is the, now there is change taking place at chiral center. So you are getting now a C plus, that is carbocation. So this is nothing but SN1 reaction. Now though here it is written NaNO2 and ACOH, that is acetic acid, but it is if you consider it as dilute acetic acid, that is acetic acid in water, then this water, it will act now as nucleophile, and which can attack this carbocation with equal facility of attacking both sides. Okay, so now we will get D plus E. So one is S, another one will be R. You can consider any of them as D plus C, but one thing is sure that you will get two enantiomer. Okay, one is S, another one is R. So that is all about this reaction. Our next question is, the hydrolysis of methyl chloride takes place much faster in the presence of sodium iodide. Now hydrolysis of methyl chloride. Hydrolysis is, if you consider the general term solvolysis, that is reaction in the solvent where solvent is itself acting as nucleophile. So then it is solvolysis. So in a similar way, if your solvent is water, you can call the solvolysis reaction as hydrolysis. In a similar way, suppose your solvent is ethanol, you can call it ethanolysis, just like that. Or methanolysis, solvent is methanol. So the hydrolysis of CH3Cl means your attacking nucleophile is the solvent itself, which is nothing but H2O. So basically here the reaction is between methyl chloride plus H2O, and the product that you can expect is methanol. Now this reaction, when you are doing in presence of sodium iodide, it is taking place at a much faster rate. But if you are not using sodium iodide, the reaction is simply CH3Cl plus H2O equal to methanol. Then it is happening at a less faster rate. So what is the reason behind that? That we have to see here. So actually here nucleophilic catalysis is taking place. So what is nucleophilic catalysis? First of all, think that there is no NaI we are using. You are simply using CH3Cl plus H2O, which is your nucleophile, and you are getting product methanol. Now H2O, if you consider as nucleophile, it is not very good nucleophile, because first of all it is neutral, and also oxygen is very electronegative. So the attacking tendency of H2O over carbon, it is not very good. And CCl bond, that is also not very weak, and Cl is also not very good Lewin group. So this reaction, it is not very fast. Now in presence of NaI, there is presence of I minus ion. So I minus ion, if you consider the nucleophilicity, obviously nucleophilicity, it is greater than water. So in presence of Na, NaI, as it is ionic, you can easily get N plus and I minus. So when there will be I minus in the reaction medium, and as it is better nucleophile compared to H2O, so it will attack the carbon and first it will form CH3I. Now CH3I, it is not the final product. This is the first step, first SN2 mechanism, and this molecule we are getting for some time. Now see, I minus, it is good nucleophile compared to H2. And another benefit that we are getting from I minus is that I minus is also very good leaving group if you compare with Cl. So when you are not using NaI, then your leaving group is Cl. But now when you are using NaI, this product is formed first. And I minus, as it is better leaving group, carbon iodide bond can be easily broken. So now this reaction, that is the second SN2, where H2O, that is our actual nucleophile, it will attack this carbon and I minus will be removed very easily. So basically here sodium iodide, it is acting as a nucleophilic catalysis. Why it is catalysis? Because it is increasing the reaction rate. And why nucleophilic catalysis? Because I minus is acting as a nucleophile in the first step. So that is why this process is known as nucleophilic catalysis. Though our final product in both cases that are same, but reaction rate, it will be high if you are doing the reaction in the presence of sodium iodide. Next problem. RBr, that is any alkyl bromide, reacts with AgCN, that is sodium cyanide, and it gives alkyl isocyanide. But if you are using the same substrate alkyl bromide, but now instead of AgCN, if you have taken sodium cyanide, now your product is different. Now it is alkyl cyanide instead of alkyl isocyanide. So what is the process that is actually happening? First we have to consider the ion Cn minus. Cn minus is actually ambidentate nucleophile, because you can see from this picture there are two resonance structures. Why it is ambidentate nucleophile? Because it can attack electrophilic centers through different nucleophilic center. There is N minus, that is also possible, so it can attack from this side, and there is C minus also in another resonance structure. So this can also act as nucleophilic center. So there are two nucleophilic center, one is nitrogen, another one is carbon. Now when the reaction is happening in presence of AgCN, basically the reaction is going through SN1 mechanism, because in presence of sodium cyanide, Ag, it is forming, it is actually promoting the ionization of RBr by the formation of solid AgBr, which will be precipitated in the reaction medium, and the reaction will move forward. So as RBr bond is easily broken, you are getting this carbocation, that is SN1 mechanism. Now Cn minus, which is we have that is generated from AgCN, because Ag plus already it is reacting with Br forming AgBr. So now the Cn minus, it will attack from the more electron dense region, that is N minus, that is it will attack through N minus. So that is why you are getting RNC, you are not getting RCN. So the attack on the carbocation, it is taking place through more electronegative and more electron dense nitrogen atom, and ultimately we are getting alkyl isocyanide. Now if it is NaCN you are using, reaction is going through SN2. Now unlike AgCN, in presence of sodium cyanide, sodium plus ion, it cannot promote the ionization of RBr bond, unlike the previous process. Okay, so that is why there is no such formation of R plus. It is going through SN2, so bond formation by the nucleophile, it is taking place, and the bond breaking of this RBr bond, that is the R and leaving group bond, that is also taking place simultaneously in the transition state. So now there is no R plus, so there is direct attack on R. Br is already attached with R. Now the attack of the nucleophile, it will take place through the carbon, that is C minus. So that is why finally what we are getting? We are getting RCN, that is alkyl cyanide. Now you can consider this process from another point of view, which is hard and soft acid and bases. So it states that hard acids prefer to form bond with hard bases and soft acid prefer to form bond with soft bases. Now in SN1, the more electronegative nitrogen atom of the ambidentate nucleophile Cn, which is actually a hard base, it will prefer to form bond with R plus because that is a hard acid. But in the second case, the more polarizable C minus in the cyanide ion, it will prefer to form bond with R in the transition state, because compared to R plus, now the alkyl group, actually alkyl group, I mean to say the carbon which is attached to Br, that is in acting as soft base. So here soft interaction is taking place. You can see I have written here SS, that is soft interaction. C minus is soft and this alkyl group now is softer compared to R plus. So R plus, it is hard, and N minus, that is also hard. So here the hard combination is taking place. So that is the difference. So you can consider the total observation from the point of view of hard acid, so hard and soft acid base concept. Okay. So these are all the problems in today's video. I hope it will help you to clear your idea about aliphatic nucleophilic substitution, and if you find it helpful, please like, share and subscribe. Thank you for your attention.